Hi, and welcome to our next section in the gradient boosting chapter. So I'll not introduce anything conceptually new in this subsection here. I'll simply want to show you a couple of visualizations of boosting and regression in order to visualize the quite complicated gradient boosting procedure with all of these iterative fits against pseudo-residuals. That was quite complicated, so I guess it's a good idea to get a better feeling now how different loss functions and different base learners impact the procedure, and in general to get a better handle on what happens in gradient boosting through visualizations and simple examples. And at the end I show a quick deep dive to demonstrate that gradient boosting on linear models is pretty much mathematically equivalent to running normal gradient descent on a linear model. Okay, so let's start. So I'll start with this univariate toy data set here. I think that's a running example through most of the slides in the subsection. So this has a simple linear trend here, what you can see, and then a little bit of sinusoidal structure on top of that, and some Gaussian noise, and we have sampled 50 points from this. And as a model, I'll use a GAM model. So if you don't know what that is, that simply uses splines as base learners. So specifically, I'll use cubic B-splines with 40 knots. And yeah, in order to introduce a little bit more, variation into the algorithm, we'll compare L2 loss versus L1 loss. We already know then how our boosting model is initialized in the first or 0th iteration. So for L2, we know that the optimal initialization constant for our model would be the mean of the target values, and for L1 it would be the median of y. As a reminder, we also know how the pseudo-residual function looks like for L2. So for L2, it's simply the true residuals, so the difference between our numerical or target value y and the model prediction. And for L1, it's the sign of the residual. So that can only be a +1 or a -1 depending on whether we overestimate the y with our f or whether we underestimate it. And I'll simply use a constant learning rate of 0.2 here. So let's see what happens in iteration 1. So on the left hand side I have visualized the current ensemble. So currently it's only has one component, a very simple one, or we could even say it's empty and it just has an intercept. And this is here this optimal constant. So at the top we always see the L2 loss model. So here it's the mean of these target values, and here it's the median. I guess we can see a slight difference between these constants, but that doesn't really matter here much. We've also visualized, of course, the data points, and here you can see the true residuals as these little sticks or bars beneath our data points. And on the right-hand side, we can see the current pseudo-residuals in the current iteration that we will now fit our base learner against. So each height of the data point here, so the x position is the true feature value, and the observed feature value simply in our training data, and the height here is the computed pseudo-residual from these two different formulas. Now, you can also see for L1 it's constant, like I said, right? So here we have minus ones, and here we have plus ones. And I guess we can also check that very well, because here in that area on the left-hand side, we are underestimating. We are overestimating our true target labels, and here we are underestimating. And here it's simply the residuals, and I guess you could calculate that if you take the first data point, and if you now compute the difference between this guy here, so that might be, I don't know, -0.8 maybe, rather -0.7. Let's say -0. So this is -0.7, yeah, and I guess you can check that for a couple of other points, and maybe check that also later when the model has become slightly more complicated than simply a constant, which is also nearly exactly 0. And if we now iterate through this here, so this is the second iteration, so we would now take this base learner here, multiply it with the learning rate, and we add it into our model stack. So in our additive model, which now has one component. And we do this for both cases. And you can see here also that the base learners are not really that much affected with respect to the size of our pseudo-residuals in the L1 case, because that only takes the sign. And in L2, we are more affected by larger and smaller pseudo-residuals. So you can see here how we now iterate through that and how our models gradually change. So this is after 100 iterations, where through both models we are fitting, or through both loss functions in gradient boosting, we are now fitting, let's say, quite well to the underlying structure of the data. Here's another example now with Huber loss. So let's make things a little bit more complicated and interesting. So you can see the Huber loss down here. I hope you remember that this is now a combination between an inner L2 shape and an outer L1 shape. So we have these L1 parts here, and the width of this inner interval that's controlled by this delta parameter. And we have taken here now two delta parameters, a small one at the bottom and the large one at the top. So the larger this delta parameter is, the more we are using actually L2 loss, and the smaller it is, the more we are using L1 loss. Pretty obvious. So for these small delta values, our pseudo-residuals are now often effectively bounded, which results more in an L1 behavior. So we could compare this a little bit with the visualizations on the slide before. So while this upper plot here resembles the behavior in L2 a bit more. So if you look at this, so this nearly not exactly, but it looks a little bit like this. Like this discrete +1, -1 behavior we have seen on the slide before for L1. And here this looks a little bit more continuous. But it's also nice to notice now that this really just goes through with a more complicated loss function and works in general as before. Here's another example with outliers. We should also now have a pretty good understanding of what would happen here. So I've now used, instead of Gaussian noise, I've used the t-distribution, so more heavy-tailed distribution, and that leads to more outliers. And why? And for this specific example we have sampled here, you can see one very strong outlier here and maybe another one here. So because of this, we can now not even really see the trend of our data that well anymore. Maybe we should have, I don't know, plotted this on log scale, because these outliers now screw up the scale of our y-axis a little bit. And what can we see now here? Well, I guess we already know that, right? That L2 loss is affected much more strongly by outliers. You can see that in the pseudo-residuals, we try to fit against these much more strongly. So we have our one guy here, and I guess that's our second more moderate outlier here. Maybe I shouldn't even mark that as an outlier. Maybe it's just that guy. And for L1, because we only take the sign now, makes it pretty obvious that we are resulting in a much more robust behavior and in a much more robust final model. And this is after iteration 100, where you can see these large oscillations here towards the outliers in the L2 case. Maybe an even simpler example now might be interesting also to study what happens if we kind of use one of the simplest models ever, which would be a univariate linear model here for this univariate data set, again with L1 and L2. What happens now? Some people are actually doing that, I guess we are going to talk about these cases a bit more in detail later on when we study component-wise boosting or model-based boosting. For now, I want to keep it simple here and say that, of course, if we use the linear base learner and we use L2 loss in the first iteration, because our pseudo-residuals are just our residuals, we will already fit a perfect model, and we are basically done in the first iteration. So if we still stick to our boosting algorithm and pattern, this optimal model would still be added in only with a kind of a dampening factor due to the learning rate, and that slows down learning a bit. But in general, we are kind of done in the first iteration, right? And as a comparison point, I've also still shown here what happens with L1.